Okay, so I'm really hoping today's video records and I can post online. I really don't know what happened on Monday. I was really sad. So thank you for your forgiveness. But yes, please watch the linear algebra videos. You can support 3 Blue 1 Brown on Patreon. No, he makes really great videos. So not just linear algebra, but he has one on neural networks, and we'll do a little bit of neural networks in this class. Okay, that's like in the coming weeks, because it's a great application of an optimization method that we'll learn. Anyway, okay. Are we ready to begin? Okay, all right. So we left off on Monday, and I said, linear algebra. Oh wait, hang on. I have to fix something here. Okay, so I said linear algebra counts as machine learning. So, I mean, in that you have a model, because all really machine learning, all it is basically training our model using data, okay? That's really all machine learning is. And so linear algebra counts because you're taking your data, your pairs of x and y coordinates, and you're using that to estimate parameters of beta 0, or in the textbook notation, w0 and w1 for the intercept and the slope. So you know, you guys all know linear algebra, so it is not a lie to say you are familiar with basic machine learning, although some might say that is unethical and misleading, because when you say machine learning, they're probably expecting something more complicated, but it's not a lie to say that. It is true. So linear algebra does count as machine learning, and we looked at kind of just a little bit of the analytic methods, and we glossed over parts of it, and we said we arrive at the best estimates of slope and intercept by minimizing a loss function, okay? And so the at our estimates of intercept and slope, intercept w0 and slope w1, by minimizing I'm going to run out of space here, loss function. And the loss function we define to be the average or the mean sum of squares residual, which is going to be the difference between each observation's output, the t sub n, and our textbook uses t rather than y, minus our fitted value, w0 plus w1 x sub n squared from n equals 1 to capital N. Okay, so this is our loss function. This is our kind of our mean squared residual. And we said, you know, we can minimize this. We take the derivative of the loss function L with respect to w0 and w1. We solve for them. We arrive at the estimates of w0 and w1 that minimize this loss function. Okay, and that's what we did on Monday. So today we're going to do pretty much, well, at least there's so much notation and stuff that we might not finish today. But we're going to do the same thing, but we're going to start working with vector and matrix notation, okay? Because this notation that we're using, W0 and W1, and multiplying them out by xn, that's perfectly fine for linear regression. But let's say we had multiple linear regression, okay? Then all of this can get very complicated. So today we will do the same. But with matrix notation, okay? And the idea being is, you know, if we did multiple linear regression, we may have something like t sub n minus the quantity w0 plus w1 xn1 plus w2 xn2 plus w3 xn3 plus w4 xn4, and it's not unreasonable to have 15 terms in as different predictor variables, okay? And we would not want to have to write out all of these terms. So wk xnk, all right? And instead, if we say the vector xn represents 1, xn1, xn2, dot, 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 to xnk, and the vector w represents w0, w1, dot, 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 all the way to wk, the above thing can just be t sub n minus the vector w transpose xn, okay? And so this, having a notation like this will certainly make our life easier, okay? But there is a hurdle in getting things into, you know, matrix and vector notation. But if we can get things into vector and matrix notation, then, you know, we can expand things out to have, you know, 15 regressors and things like that, and it's okay. All right, so this is what we're going for today, and then we'll, if we get to it, we'll take derivatives in vector notation, and that we're doing the same thing. We're doing the same thing, just with new notation. Okay, so are we ready for this? Okay, great. Okay, so just to keep things simple, we will still do linear regression with just one predictor. Okay, so so kind of our original linear model is going to be, we've got, so for some observation n, we've got t sub n is equal to w0 plus w1 xn. Okay, so this is our predicted, you know, our output there. Okay, and so we will have two vectors. We've got vector w. Let me try to just write a little bit neater. Vector w, which will be the values w0 and w1. And then we have the vector xn, which is going to be the value 1 and xn. Okay, and so our fitted value, which is a function of the value xn given parameters w0 and w1 is equal to W transpose xn, which is equal to W0 plus W0 W1 times 1 xn, and doing matrix multiplication, we get W0 plus W1 xn. So that's exactly what we want. Okay, so now we can use this to replace anything that we used to have. So what we had was our loss function was written as L is equal to 1 over n times, times the sum of t sub n minus the quantity W0 plus W1 xn quantity squared from n equals 1 to capital N. And now we can just say, well, we can replace this with this. So this is going to become 1 over n equals 1 to n of Tn minus W transpose xn quantity squared. Okay, and this is vector notation. Yet we are still not yet harnessing the power of matrices. And what we will do next, the next step, and I'm going to have to explain how we get to this next step, is then to do the entire summation part, and this is going to become T transpose minus the matrix X W times okay, but the next slide will say how we go from how we make this jump from here to here. I mean, maybe you guys can see it already, but I'll explain. Okay. Is it just me, or the lights in the? Do I see like yellow next to the? Or I don't know. Maybe my eyes. Huh? Might be the angle. Yeah. All right. I don't know. Okay. All right. Everything so far so good? Great. Okay. All right. So how do we do this? What we're going to do is we're going to define our matrix X. Our matrix X is going to be 1 and x1, 1 and x2, all the way to 1 and xn. Okay. So this is an n by 2 matrix. Okay. And this can be thus rewritten as x1 transpose x2, the vector x2 transpose ... all the way down to the vector xn transpose if you so desire. Okay, and we'll also let the vector t just be the n by 1 matrix of all the t values, t1, t2, all the way to t capital N. Okay, and again, recall that the W vector is W0, W1. Okay, so if I have x times our W vector, we have exactly this. 1x1, 1x2, dot, 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 to 1xn times w0, w1, which will give us, so I've got a n by 2, and this is a 2 by 1. What's the dimension going to be of our output vector? N by 1, and it's just going to be the sum, or the quantities, w0 plus w1 x1, w0 plus w1 x2, all the way down to w0 plus w1 xn. Okay, and this is a n by 1. All right, and thus t, the vector t minus xw is going to be the quantity t1 minus w0 plus w1 x1, t2 minus w0 plus w1 x2, down to tn minus w0 plus w1 xn. Okay, and then if I were to, so this also is an n by 1, and if I were to take the these matrices or these vectors, and do this times okay, so here when I transpose, this would become 1 by n, and this becomes n by 1. We're going to get a 1 by 1 scalar output, right? And this is going to be effectively, basically, the sum of all the elements squared. So it's equal to the sum of t sub n from n equals 1 to capital N minus w0 plus w1 xn squared. Is that it? There's a squaring term. We're all okay? Good? All right. This is it took me a while to gain an appreciation for linear algebra, but now it's like, it's the best. So, next to statistics, right? And these are like my, sorry. Now, I just breathed through my nose, but it sounded so loud. Okay. All right. Can I go to the next slide here? Great. Okay. So what we have now is we've now defined our loss function is 1 over n times the vector t minus x and w transpose times t minus the matrix x w. Okay, and this we said is the output is a 1 by 1 scalar. Okay, so now I'm going to kind of expand this out. All right, we're gonna 1 by n, and kind of using the properties of transposes, this is going to become T transpose minus XW transpose, okay, times T minus XW, okay. And then now we have to expand all of this multiplication, which is a little bit crazy, but it's okay. All right, so we got T transpose T, right? Foil it right first, and then you do the outer, so you get minus T transpose XW, and then inside we get XW transpose T transpose, and then lastly we have XW transpose XW. Okay, it's okay. And then and if we look at oh, what happened to my color? Okay. This element and this element, these can be combined. Okay, so here's a little bit of an aside on how those two things can be combined. So if I take this XW transpose T, so applying the transpose, this becomes W transpose X transpose T, bless you, okay? And, okay, and if we think about this thing, if we look at what is this output here, this is a scalar output, because W transpose is going to be 1 by 2, and X transpose, X is n by 2, X transpose will be 2 by n, and T is n by 1, right? So when you multiply all of these out, this becomes a 1 by 1 scalar, which means I can take a scalar and I can transpose it and it has no effect, right? So it's totally okay. So if it were not a scalar, this would not be allowed, but because it is a scalar, it is allowed. I can just take this whole thing and transpose the whole thing. Okay, which applying the transpose rules becomes T transpose X and W. Okay, and that combines with that. So if I take this and I just kind of expand things out, they can be combined. And apparently, well, it doesn't matter. Okay. So this becomes 1 over n, and here I have T transpose T minus 2 times T transpose X W plus, and then if I just kind of expand this out, W transpose X transpose X and W. Okay, and we can check on everything, and this is 1 by n times n by 1. Okay, so this becomes 1 by 1, and this is 1 by n. This is n by 2, and this is 2 by 1. So this also combines to be a 1 by 1, and w is going to be w transpose is 1 by 2. X transpose will be 2 by n. X is n by 2, and w is 2 by 1. And so all of these combine also to a 1 by 1. Okay, so everything becomes, you know, a 1 by 1 scalar output. Which is what we want, okay? Because this is our loss function. So not to lose sight of the big picture, this is just our loss function. We're getting a way to measure how good our estimates W0 and W1, when we feed that in, when we combine that with the data and, you know, the input data, the X's, and the output data, the T's, we get a measure, a single value measure of how good this fit is. That's our loss function. It's defined as the average squared residual. Okay, so this is what we have. This is our loss function. Okay, in matrix notation. Great, great. Okay, and so now what we're going to do is I have to kind of introduce the idea of, now we're going to take the derivative of this thing with respect to the vector w. Okay, so we have our loss function. In vector matrix notation. Okay, and we want to find the minimum of the loss function, right? And so the way we're going to do this is we're going to take the derivative and set that thing equal to 0, or solve for where the derivative equals 0. Okay, so Did you guys take derivatives with respect to vectors in linear algebra? Okay, so we're all good, right? With gradients and stuff, maybe? Well, okay. Well, anyway, we'll do a quick review of this. Okay, so just so here we want okay, so we will take a derivative with respect to a vector. Okay, and so what we have is just kind of the loss function that we have is a function of two things. Okay, so one is our data output vector t, and kind of our, basically our model's predicted values. Okay, and it measures kind of the difference between these two things. And the model's predicted values itself is a function of in the input matrix X and parameter vector W. Okay, so the loss measures kind of the difference between the output vector T. Should put a little arrow over that. The output vector T and the predicted values, which itself is a function of the input values in the matrix X and the parameter vector W. Okay. Our data, which consists of the output vector T and X, are treated as fixed values. And we can only alter W. So, we want to see how the loss function changes with respect to W. Okay. Okay, and so a derivative for a function with one variable, the derivative tells you how the function changes with respect to that one variable. Now that we have a function of a vector, the derivative or the gradient of that function tells you how the function changes with respect to each component of the vector. All right, so I should write this. Okay, so with a function of a vector, okay, so this is our loss function. If we keep everything else constant, then the only thing that can change being W. So with a function of a vector, the derivative or gradient of that function And so the gradient itself is a vector. Okay? The gradient itself is a vector. Can I go on here? No? Not yet. Okay. We'll wait. We'll wait. Don't look so sad. Okay. So basically, if you understood what we did on Monday with the partial derivatives, we're pretty much doing the same thing here, except we're just doing it in matrix notation, okay? So we're just saying, how does everything, because if a partial derivative is just how does the function change with respect to just that one, I don't know, thing in the multivariate function. Here it's the same idea here, okay? I'm gonna do, just to kind of, I don't know, write it a little bit, okay? So our loss function what it does, the inputs are, in this case, n-dimensional. In our case, it's n is equal to 2 because we have w0 and w1. We have two values in our w vector. The inputs are n-dimensional, and the output, so it goes into our function of w, and it outputs to one dimension. Okay, so we could say that, so mathematically we would write this, that function maps from n real space to just regular real space, right? And that's the rule of a function, right? Whatever inputs you have, it can only output one thing in order for it to be a function. And that's what we have. We've got n-dimensional input. In our case, we've got a dimension 2. That two-dimensional thing outputs to 1, okay? The gradient, okay, the gradient of f with respect to w, okay, we would write this as the gradient of f. We can think of this as this, and this would be the kind of the partial with respect to kind of each component here. W0, W1, and if you have more, maybe transpose. This is going to be an element, so actually let me rewrite this from just 1 to just so it goes to n. This is going to be an element in space, okay? So the gradient itself exists in n-dimensional space, okay? And each element is a partial derivative. So we could say partial with respect to w sub I is effectively, if you recall the definition of a derivative, it's 1 over delta times the difference between W1 all the way to Wi plus delta. Okay, so it's basically just all the components of W, but you've just perturbed one of the elements ever so slightly, and you wanted to see how does that affect the function. So you're just adding a tiny bit, a tiny delta to just one of the things, and how does that affect the function? And the amount it changes, as that delta gets smaller and smaller and smaller, is going to be your partial derivative. Yes?
So F here is our loss function, not the model.
Well, this f here is just a general function, okay? In our case, yeah, we're looking at a loss function where the inputs are two-dimensional vectors of w0 and w1. But in generally speaking, we could have any function f of an n-dimensional input vector, and then the gradient with respect to that n vector in n space is going to be another vector in n space. Maybe we'll just do a simple example. I think we're going to run out of time, so we won't get to do the actual gradient of the loss function that we're talking about, but let's just try a simple example. Of a gradient. Okay, so let's say we have some function of w where w is an element of two-dimensional real space, okay? And this function is going to be w1 squared plus w1 w2 squared. Okay, and I could ask, what is the gradient of f at 1, 1? Okay, so this would effectively be the vector and transpose, okay? And so here we would have, so if we take it with respect to w1, I would have 2 w1 plus w2 squared, right? And then if I take it with respect to w2, I would have, this becomes 0, and this becomes 2 w1 w2. Is that okay? And so the gradient at the point 1, 1 is going to be basically this evaluated at the point 1, 1. And so I get 3, 2 transpose. So you have basically a surface over W1 and W2, and this tells us kind of the direction of how the that surface changes. All right. Okay. Well, is that okay?
Yep.
All right. We'll end here today. I promise it will get exciting in all of this, right? Okay, so we'll end here, and we'll see you guys on Friday.